go.
All right. Thank you so much for the introduction, Shelly. And hello, everyone. I'm really excited and happy about being here. And thank you so much for having me and joining to this workshop with me. So as Shelly said, I'm a second year PhD student at WashU. I study cognitive psychology broadly. And today we are going to talk about iterations in R. And let's go. If you haven't downloaded the materials yet, you can just go to GitHub account of Our Ladies quickly and download the materials. When you open it, you will see this code section, and when you just click download zip, it will download all the materials. And these three are the main materials we will use today. The first one is just the slides. So just for you to be able to reach out to them after the workshop if you want. And the other two are our Markdown files that we use for the code and for the exercises. And you can see there are two versions, one with the solutions and one without the solutions to exercises. And after I introduce the concepts, we will do lots of exercises, and I suggest you to try to do the find the solutions on your own first. I'll give you some time for this, and then we will go over the solutions together. So let's start with why should you even attend to this workshop? And the basic reason, the main reason is that you want to learn how to speak to your computer, because your computer doesn't speak in English or in any other language that you speak. You need to find a way that will translate what you want to do in a language that your computer would understand. And that's what we do basically with programming languages. Because for most of the time, you know what you want to do with your data or with your settings, but you need to translate this to a way that your computer will understand. And today we will talk about them. How would you communicate with your computer? And it will allow you to understand the basic logic of programming. So the concepts we will talk about today are not limited for R. Of course, there are different syntax for R and for different programming languages, but the basic logic and the general idea are pretty similar across programming languages. So today, hopefully you will better understand the basic logic of programming. So why do you need iteration? Let's first think about that. And to understand that, we should first ask, what does R normally do when running a script or when running a code? So it starts from the top of the script, top of the file that you have, and run the code line by line until the end, and then it stops. It just basically reads the script one by one. But for so many times, you want to do the same thing, same operations for several times with multiple conditions. For instance, you need to do the same thing for different participants, different data frames, different columns or rows. And it is not efficient to just copy paste what you want to do again and again. Instead of copy pasting and duplicating, you can use iterations or loops that are a sequence of commands that R will execute over and over again until some termination criteria are met. So we will give a set of statements to R, and it will run this for different participants, different columns, or different conditions that we define. So the main aim will be reducing duplication and having more efficient codes. Overall, iterations will help you to have more readable codes, because when you have a very long code, it will be harder to read and understand it. So obviously it will make you save time, and also it makes it easier to change your codes, because let's say you wanted to make a change in your code, or maybe you made a mistake in a part of your code. If you just copy pasted it for different participants or different conditions, then you need to make these changes to several parts, which makes it very open to make errors. But when you have iterations, when you just change as one part of the code, it will be changed for all iterations, which will also reduce the errors. So today, first we will talk about conditional statements before starting to talk about iterations for loops, because conditional statements will be very useful when we are talking about for loops or when we write functions. And just in case you may not be familiar with conditionals in R, I just wanted to briefly introduce them. And then we will talk about for loops, which are the most common type of iterations we use in R, and it is common to so many different programming languages. And finally, we will talk about how to write our own custom functions when we need to create a new function. I'll have lots of exercises for you. So after introducing the basic idea of these concepts, we will switch to R and do some exercises. And when it is general to programming, being able to read code and understand someone else's code is a different skill than being able to write your own code. So it is easier to understand when someone explains to you what they do in a code, but it is harder to do this on your own. Even very simple things, just like when to put the parentheses or curly brackets, they are really open to make errors. So it is very useful to try to write them on your own. So for the exercises, first I'll give you some time for you to try the solutions on your own, and then we will go over the solutions together. But I have a lot of exercises, and probably we will not be able to get to all of them, but I still wanted to add them so that you can check them out later. And I also have some extra concepts both in the slides and in R, which are while loop, which is a different version of iterations, and implicit loops. I'm pretty sure we will not be able to get to them, but I still wanted to add them so that if you are interested in, you will have some resources and you can check them out later. So let's start with the conditionals. Conditionals are basically if-else statements, and we use them to switch between different possible commands depending on a condition that we specify. And this is the basic syntax of if statement. First, you write if, and then in parentheses, you define a condition. That condition needs to produce a logical value. So it should either return true or false. And when you write a if code, if statement, the first thing I do is checking if the condition is true. And let's quickly remember what kind of logical operators you can use in R to check the condition. Basically, you can just use something like less than or equal to, or greater than, or exactly equal to, or not equal to. And you can use more complex condition. It doesn't have to be just one condition, but you can combine different conditions with an or statement or with an and statement. So after R checks the condition, if it produced the value true, it goes on to this curly brackets and execute all the commands inside the curly brackets from top to bottom. And when it gets to the bottom statement, it stops and just continue with the next part of your code. But if the condition returns the value false from the beginning, then it doesn't execute the command inside the curly brackets, and it just jumps and skips this if statement. And for so many times, because we want to switch between different possible commands, we want to have an else statement to tell the R what to do if the condition is not true. So for this, the first part is exactly the same. We are just writing if and then state a condition. And then in the curly brackets, we define what to do if the condition is true. So if the condition is true, R just executes all the commands inside the curly brackets that belongs to if. And if the condition is false, it goes on to execute the commands inside the else curly brackets. And when it gets to the bottom, again, it just stops. But we can also have some additional conditions. So it doesn't have to be either this or this, but we can have several different else if statements. So in this example, after giving a if statement, after testing the first condition, we can make our test another condition. And to do this, we write else if, which means if the first condition is not met, check this condition. And if the first condition is false, but the second condition is true, R will execute the commands inside the else if curly brackets. And if none of the conditions are true, it goes on to the else statement and execute the commands inside the else curly brackets. So you can increase the number of else if statements as much as you want. So do we really use conditionals? Or in other words, do we really use them in real life? Or are they just something that we learn and then never use? And the response is definitely yes. We use them a lot. And just to show you a simple way how I use it in my data is I use it to decide if I want to include a participant or exclude. You don't need to worry about the code here. You don't need to understand it. It's just to give you an example. So in this code, I just say, compare the error of a participant with a criteria I have, which is more than 3 standard deviation of the average error. And if this condition is met, it means that this participant has so many errors that I want to exclude them. And I just say, then I want to exclude this participant. I want to update my data. It's a very just simple way of using if, and we specifically use them a lot in our loops or in our functions. So let's do some exercise in R and show some examples, which will make it much more apparent to you. Now I switch to the R Markdown file that I share with you, so you can also open it and follow with me. I'll just wait for a second for everyone to open it. All right. After you open it, you will see there are some little gray chunks that we call as code chunks. In these gray boxes, I have my codes. So R will execute everything in these gray boxes. So when I type something in this gray boxes, it means it is a code. If I want to add something that is not a code, just like an explanation, I use this hashtags to make it a comment. So it will not execute these lines, which are stated as a comment, but will execute these lines. And you will not need to create new code chunks. I already have all of them, but I just want to show you quickly some shortcuts that will be useful for you. To insert a new code chunk in Windows, you can use Control Alt and I. So when I just do this, it creates a new code chunk, and then I can type a new code here. So for Mac, you need to use Command, Option, and I to create a new code chunk. And when you look at one of the code chunks, you will see this little red green run button. When you click this, it runs all the codes inside this chunk. But for so many times, especially for a workshop, I prefer running the code line by line, so it will be easier to follow them. And to run only one line of code, you can use Control and Enter shortcut. And Windows and Command and Return for Mac. So when I click here, my cursor is selecting this line, or I don't have to click the start of this line. I can also click here or here, it doesn't matter. And then press Control Enter, it run this line, and then it switch to the next line. And if I just like press Control Enter again, it will run this line. And one more thing that I want to show you before starting is switching to Visual Markdown Editor. So there's a little button at the right top, which looks like an A. When you click this, so it's switched between different types of editors. Now it is a source editor. And when I click this again, it's switched to Visual Markdown Editor. So I just suggest you to use this in Visual Markdown Editor because it is much more readable in this version, and it is also easier to format. That's anything you want to do here. So these were just some little notes, just in case you're not familiar with our Markdown. And now we can start with conditionals. Let's define a variable first to do some examples. And again, if you are not familiar with it, this arrow basically means equal in R. And when I do this, I say I want to create a variable which will be named as X, and I want to give the value -6 to this variable. So I run this line and I created this variable that I can see in my environment. Now I want to write an if statement that will check if the X is a positive number. So to do this, I first write if, and inside the parentheses, I define my function. Because I want to see if it's a positive number, I'm just asking, is X greater than 0? And if this condition is true, if it returns the value true, it will execute the lines that I included in this curly brackets. And in them, I just say print X is a positive number. So let's run this line. It didn't do anything because it checks the condition. It looked if X is greater than 0, and it is not. So there's nothing that R can do here. We asked a question and the question gave the response false, so it didn't execute the statements inside the curly brackets. But if I want R to do something, if the condition is not true, now I need to include an else statement. So the first part is the same. I'm just asking if X is greater than 0, print X is a positive number. Else, if X is not greater than 0, then print X is a negative number or 0. When I run this code, I can see that it prints here and also in my console that X is a negative number or 0. And something that you need to be careful about is when using else, it should be on the same line as the closing bracket of if. So if I just like put this to another line and then run this statement, it again didn't do anything, because when I don't put the else statement right after the closing brackets of if, it doesn't recognize if there's an else statement, if the if statement continues. It just thought if statement ends, so it didn't do anything. So as I mentioned, you can define more conditions. It doesn't have to be either this or that. To define more conditions, I can use else if statement. So here I say if X is greater than 0, print X is a positive number. Else if the first condition is not true, then check the second condition, which is X is equal to 0. And if it is true, print X is 0. Else, if none of them is true, then print X is a negative number. So when I run this, it prints X is a negative number. Let's do another example to better understand how this else if statements work. Now I'm updating the value of x and say now x is equal to 10, and I can see that in my global environment, the value of x is updated. Now I want to test if x is divisible by 2 first. So these 2% signs in R means modulo division, which is just basically tells the remainder of a value when it is divided by another value. So it just checks when we divide x by 2 if the remainder is 0, which means x is divisible by 2. I say first check this condition, and if the condition is not true, check another condition that I indicate with else if, which is the x is divisible by 5. Now I'm again using modulo division for 5. Else, if none of them is true, just print x is divisible but is not divisible by 2 nor by 5. So when I run this code, it says x is divisible by 2. But actually, this code doesn't make much sense because it checked if the first condition is true. And because it was true, it just print the statement and end the loop and just stop running. But actually, if it continues, it will see that x is also divisible by 5. But when a condition is true, R just ignores the rest of the conditions. And it is specifically important if your conditions are not mutually exclusive. So you should be careful about the way that you define the order of your if-else statements, because when it finds a value that returns true, it will just ignore the rest of it. Now let's do another example. First, again, you don't need to even worry about the code. I'm just taking the date and then the day from the system clock. And then I want to create a if-else statement that will print yay if it's a weekend day and oh no if it's not. So now I just want to show you that the condition doesn't have to be just one test. By using this or sign, I can include different statements, and I can say control if the day is equal to Saturday, and also control if the day is equal to Sunday. And if one of them is true, print this statement. Because I used or here, it is enough if only one of the condition is true. But if I use and in another if-else statement, it will be required to have two true statements or 3 true statements. So you can have conditions as complex as you wish. And as I mentioned, you can also have multiple else statements. It is not limited to only one else if. If you want to control multiple conditions, you can have else if conditions as much as you want, and it will just check them one by one, as we see in the previous examples. If one of them is true, it will not continue with the remainder ones. It will just stop. So now I define a value 4, and then I say control if it is greater than 20. If it is not true, then control if it is greater than 10. If it is not true, again, now control if it is greater than 5, and so on. If none of them returns the value true, then just print it is less than 5. And finally, I also want to show you a short vectorized version of if-else statements. It is not always very useful, but when you want to do something just simple, when you want to test a simple condition and the statements that you will run depending on this condition is simple, you can just use this short version. It is basically just if else, and in the parentheses, the first argument is the test, so the condition that you want to check. And then after a comma, you indicate what to do if the condition is true. And for the third argument, you tell what to do if the condition is not true. So here I define a vector called grades, and I just gave 4 elements. I just put 4 elements into this vector, and I also gave some names to these elements. Now I want to check if the grade is a pass or fail. If the grade is smaller than 60, it means it is a fail. And if it is not smaller than 60, it will mean a pass. So when I just write if else grade smaller than 60, the first argument is my task. The second argument is what to do if it returns the value true. And the third argument is what to do if it returns the value false. So when I run this code, it shows me the pass or fail values for each element of this vector. We can also have nested conditionals, which means we can nest if-else statements into other if-else statements. And when we do this, it will execute them step by step, checking the conditions. And specifically here, how we use these curly brackets are highly important because they define what this statement, where this statement belongs to, which if and which else statement. So let's first define variables x and y, which are for and red. And then I want to start my if-else statement by checking if x is equal to 4. And then when I click this, I can see that the closing bracket of this if is here. So if the first condition is true inside the if, it will execute these lines. And if the first if is not true, it will jump to the else statement. And again, when you click here, you can see that the closing bracket is here for the else statement. It will execute these lines. So let's go one by one. First, it checks if x is equal to 4. If it is true, it jumps inside the curly brackets and it sees another if-else statement. It asks if y is equal to red. So if I have the response true here, it means that I got the true response to the first condition and also to the second condition. So I'll print x is 4 and y is red. Else, now this else is belong to the second if. I can see that from the curly brackets because the curly bracket of if ends here, and then I start this else statement. It says, so if x is 4 but y is not red, I come here and print this statement. It says x is 4 and y is not red. If the first condition is not true from the beginning, it will never goes into this if-else statement because it belongs to the first if, and it will just jump to the else statement of this if and check the second condition here. Again, it asks if y is equal to red. And if I got the response true here, it means that the first condition was not met, but the second condition was met. So I print this statement, x is not 4 and y is red. Else, if the second statement also returns the value false, it means that x is not 4 and y is not red. So it can be a bit confusing when you have multiple if-else statements, but it will become much easier as you practice with them. So you just need to follow where these curly brackets start and end to understand the borders of what if I'm referring to now and what else I'm referring to now. So when I run this code, it prints x is 4 and y is red. We have an exercise here for the if-else statements. And here I want you to try to find out whether the number is even or odd. So first we will define a number, and you can just say number is equal to 3. But I also wanted to show you an interactive way to do this. When you use this code with the prompt, when I run this, you will see it prints a prompt in the console. So it asks the user to give a number. So I can just say 6, and then I will see the number defined as 6. You can give another number. It's just like an interactive way. And now I'll ask you to try to write an if-else statement that will give you if the number is even or odd. And I'll wait for like 2 minutes for you to try on your own first, and then we will continue together with the solutions. I'll just mute myself and we will meet again in 2 minutes. All right, I'm back. Let's continue with the solutions. And if you don't want to like try to write them on your own, it is also just enough if you think, how would you solve this problem? Just like hypothetically. Now, we just defined a number here. Again, just like, let's do it again and ask me a number, let's say 4. And then I want to write an if-else statement to check if this number is odd or even. And I can just simply use modulo division. If when I divide the number by 2, the remainder is 0, it means my number is even. If it is not, it means this number is odd. So first I just type if, and inside my condition, inside the parentheses, I just say modulo division 2 is equal to 0, and then I opened a curly bracket to tell R what to do if this condition is true. And then I say print the number is even. This paste function here allows you to print a statement with a dynamic variable in it. So when I use paste, it didn't actually print num is even, but it printed like 5 is even or 5 is odd. So it changed the value of num depending on what you have. And inside these quotation marks, it is just a text that I want to paste. And I say else, if the number is not even, so when I divide this by 2, the remainder is not 0, print it is an odd number. So sorry, it was probably something that stayed from a previous try. So when I just run this, now it told me 4 is even. And we can also try another version with if-else statement, because it is a pretty simple if-else statement. I can use the short version. First, I just type the condition that I have, and for the second part, I just tell what to print if the condition is met. And for the third argument, I just tell what to do if the condition is not met. And when I run this, again, it just tells me even. So now we will continue with the for loop. I'll switch to my slides. And yes, so the for loop is one of the most commonly used version of iterations, not only in R, but in so many different programming languages. And the basic thing it does is running a set of statements for a fixed number of times. So here's the syntax that we use in R. First, I type for, and inside the parentheses, I say variable in vector. So let's see what it means. It means each element of the vector corresponds to a possible value of the variable var. So in the first iteration of the loop, var will be given the value that is the first element of the vector. And the statements inside the curly brackets will be run in the case that var is equal to the first element of the vector. And when it gets to the bottom statement, it will move back. It will not end as like a usual code that we would have in R. That's why it's a loop. It just moves back up and update the value of var as the second element of the vector. And then it will run the statements inside the curly brackets when the variable is equal to the second element of the vector, and so on. Once it exhausted all the values in vector, the loop will terminate and goes on. I want to briefly show you a statement that you can use in for loops, which is break. When we use break, it allows us to stop the loop before it exhausted all the items in vector. So maybe you have a special condition that you want to stop running this loop, and with break, you can just define that. That's why it is useful with when we combine with conditionals. You can define some conditions that you want to break this cycle, break this loop, and not run this anymore. And another statement that we use in for loops is next, which next, we are not terminating the loop, but we skip an iteration, a cycle, and continue with the next variable. So when you use next, again, you can use it with combined with conditionals and set some conditions that you want to skip this iteration and just continue with the next cycle. So again, the question is, do we really use the for loop in real life? And definitely yes. I always use them. They're really useful, specifically when I want to just run the same data cleaning, let's say, for all participants, or when I want to calculate something for all participants, all conditions. And here's just an example of how I use for loop. It is a relatively more complex code, and you don't need to worry about it. You don't need to understand anything in it. You can be just like ignore everything in it. I just wanted to show this to give an example how I use for loops. And here I just want to calculate a score for each participant, but I don't only want to calculate it for each participant, but I want to calculate for each level of all the factors I have. So if I want to do this manually, I will need to manually duplicate codes for so many times, it will be really inefficient and it will be very open to make an error in one of these codes. But here, I'm just using some nested for loops and I'm iterating over so many different objects, so many different vectors, which allows me to calculate the scores for each different sub-level. So let's do some exercises in R again, which will make it much more clearer for you how to use the for loop. Again, I'm switching to my R Markdown file. You can switch and follow me. So in the first example, let's see how we write this code. First, I type for, and then inside the parentheses, I say, I give the name I to my variable. It can be anything. It doesn't need to be I. It doesn't need to be X. You can just give any name. I'm just like giving a name for the variable. And then I type in. You always use in here. And then define a vector. I define the vector 1, 2, 3. So it is just a vector with 3 elements, which are 1, 2, 3. So I want that I will iterate over this vector. So in the first iteration, I will be 1. And then I execute the lines inside the curly brackets. Then I will go back and update the value of I. In the second iteration, it will take the second element of this vector. So in the second iteration, I will be 2. Then again, I will run the code inside the curly brackets. Then I will go up and update the value of I as 3, and again, run the codes. Now, because I finished all the elements inside this vector, there's nothing more to iterate over, and I just stop the loop and then continue with the next code. So when we run this, you will see that it just prints Our Ladies for 3 times. And you can see that we actually didn't use I inside the curly bracket, inside the statements. It just defined the number of iterations that we will do. For so many times, we use the variable that we define inside the loop, but it is not necessary. It just tells for how many times that I want to run this iteration. And I'm just printing Our Ladies in all iterations. Now here's another example. I say iterate t over a vector from 1 to 4. So now I will have 4 iterations. And in the first iteration, t will be 1. In the second, it will be 2, 3, and 4, and so on. So now I will use t inside my curly brackets. And in each iteration, I just want to print t. So when I run this code, we can see that it just printed 1, 2, 3, and 4, that updated t value, and that's all. And you don't, we are not restricted to numeric vectors. So in these examples, the vector that we iterate over was vectors with integers, but it is not necessary. We can also iterate over a text or character vector. So now I define another vector with different text, different character elements in it. And for those of that are not familiar with, this C is just allows me to create a new function by combining these elements. So I just use this to define a new vector. So when I run this, it created a new vector, which is called fruit. And now I say for I in fruit, so I want that I will iterate over fruit. I will take the first value of fruit and then the second element of fruit and the third element. And then I will just like print each element in each iteration. In this example, you can also see now I defined the vector outside of the loop. In the previous examples, we defined the vectors inside the loop, but again, it is not necessary. I can just define a vector outside and then just use this vector inside the for loop. Let's do another example. Now I say first again just type 4 and then say I will take the values from 1 to 10, and in each iterations I want to print I squared is whatever I squared is. So when I do this, it just printed that for it just calculated the I squared value for each I and then printed these statements. And in these examples that we did so far, we actually didn't store any variables that we created. So we just say print this, print that, or calculate I squared, but we didn't store these variables, so we cannot access them after running the loop. It just printed them and then it lost. If we want to be able to store a variable, if we want to be able to access to a variable after running a loop, then we need to define a variable and we need to initialize an object that will become our output. So let's do an example for this. Now I create an empty vector. Again, I'm just using C, and inside the parentheses, I don't put anything, which makes this an empty vector. And my vector is called squared numbers. Now I want that I will iterate over 1 to 10. And in each iteration, it will define the squared numbers as the I squared. So when I do this, I can reach out to my object later because I initiated an object and then I stored a variable inside this object. And when I say print squared numbers, it just gave me 100. So what this code does is it just run this loop, run this iteration for all I values. And it just stored the final value that squared numbers take. Because in each iteration, we updated the value and we actually overwrite to it. And for most of the time, it is not useful. We don't want to overwrite to a value, but we want to save all the output for all iterations. Let's see, how can we do this? So now, again, I'm just creating an empty vector first. And then I say, again, I will take the values from 1 to 10. But now I'm using indexing with these brackets and define the position of the elements. So again, if you're not familiar with that, when you use these brackets, it means that you are defining the first element of a vector or the second element of a vector. And because I'm also updating the value of this by I, in the first iteration, it will say squared numbers 1 is 1. So it will say the first element of squared number is 1. And when the I is updated, I will define the second element of squared numbers. So we will not overwrite to previous values, but we are populating the vector by indexing, by defining different positions. So when I do this and print the squared numbers, it shows me not only the final value, but all the values that I have during these iterations. Now, again, let's create an empty vector to see a different version of it. I again have the squared numbers with indexing, so we are populating the vector. We are just like defining the first element, second element, third element, and so on. And now I put the print statement inside the loop. When I do this, you can see that it printed whatever they have so far in this squared numbers vector in each iteration. So when you put the print statement inside the loop, it prints in each iterations, of course. So you should think about when you're doing something. Most of the time, you just want to print the final outcome, but sometimes you may want to see the next what you will have in the current iterations and print the values in each iteration. So you can think about what makes sense for your aim. And we are not restricted to vectors when we want to iterate over a sequence. It can be several different objects. And one example is we can create a list with 3 different types of elements. One element might be character, and one might be a numeric vector, and one might be logical. So I use the list function to create a list. And the first element is basket with character vector. The second element is money with numeric vector. And the last element is purchase with a logical value. So when I do this and then iterate over the elements in fruit list and print that, I can see I can just iterate over whatever I want. It doesn't have to be just the same type of values or only the numeric values or only the text values. We will continue with another exercise, but before starting to exercise, we can take a short break for maybe 5 minutes. So, and then we can meet again. And I can also answer any questions if you have during the break. So I'm now muting myself and yeah. All right, let's continue with the second exercise that we have for the for loop. Again, I'll give you some time for like 2 minutes for you to try this on your own first, and then we will go over the solution together. So now it asks how to find the number of odd numbers in a vector. So we already did something similar. We said if a number is odd or even, but now we need to count the number of odd numbers in a vector. So the hint is you need to have a variable that will keep the track of the number of total odd numbers. Let's say again 2 minutes for you to try on your own, and then we will talk about the solutions together. All right, let's go over the solution together. First, I define a vector to just test my for loop. I'll just use this vector, but you can define any other vector. It is not important. As I said, now, again, we want to check if a number in a vector is odd or even. So I'll use an if statement to check this. But I'll also need to update a value depending on the condition. So if the first number is odd, I want to make my counter variable 1. And if another variable is odd, then I want to update the value of my counter variable. In the problems like this, in the problems that you need to find the number of something, that you need to keep track of something, the concept of using a counter variable is really useful, just to count something. So first, outside of the loop, I define a variable that I use as my counter, and I say odd number is 0 because I'm just starting with 0. And if I find some odd numbers, I'll just update the value of it by adding a 1 for each odd number. So let's look at the inside first. I want to control if I divide to an element, an object by 2, the remainder is 1. So it will show me that it is an odd number. And if this condition is true, I want to update my odd number value by increasing 1. I just use equal here, but it is the same as using this. It doesn't change something. So I want to do this for each element in my vector because I want to see if the first element is odd, if the second element is odd, and so on. So I say for I in X, so I will take the value of X elements one by one, check if it's an odd number, and if it is an odd number, just update the value of odd number by increasing it 1. And at the end, print the number of odd numbers. So when I do this, it shows me I have 4 odd numbers in my vector. All right. So the next thing that I want to show you is nested for loops. As we did in if-else statements, we can also nest for statements. Okay, there's a typo. It should be just for statements. And oops, it was not a typo, but it's okay. So we can just nest for statements inside other 4 statements. And when we do this, it will first execute the first 4 and then complete everything inside it, and then goes back and execute the second 4 and so on. So when we do an example, you can understand better. Here I have a for statement first, and I just update the value of I from 1 to 3. And inside it, I have another for that I update the value of j for 1 to 3. And I want to calculate a new value, I, a, as I times j. And then I want to print all of them. Let's run this. And when you do this, you can see that in the first iteration, the I value is 1 and j value is 1. In the second iteration, I is 1 and j is 2. So when the first for loop takes the first element of the vector, it completes everything inside the smaller, more inside for. So it completes 1, 2, 3 of j for I is equal to 1 first, and then goes back and make I 2, and then give the change the value of j as 1, 2, 3, and then goes back again, make I 3, and then update the value of j 1 by 1. So let's continue with more examples. And you don't need to know the number of elements in a vector. So you don't need to say from 1 to 5, from 1 to 10. Especially when you are working with a large data set, you don't need to know how many columns or how many rows you have. You just use length function for this, and you say, I want to do this. I want to run this loop for as many data points as I have. So it can be 100, it can be 200. So I just don't need to know the exact number of iterations, but I can just use the length function to define how many iterations I need. So now I just define a vector first, my vector, and then here I say I will iterate over starting from 1 and goes to the length of my vector. So it will be goes to 5 because I have 5 elements here. And then I will define a value A and then print it. It is not something different as it's just like a simple calculation that I want to show. And here, the value I we calculated is independent from the identity of the elements because we just use the length of my vector. So we just put actually 5 here. It is not related to what you have inside these vector. It just takes 1, 2, 3, 4, 5. And if I want to use the elements in a vector, then I need to use indexing. So here I'm doing something very similar. I'm using the length of my vector, but now to calculate A, I'm not saying, as I did here, I times I, but I say my vector I times my vector I. Again, these brackets means I'm indexing a variable in a vector. So if I is 1, it means I'm taking the first element of my vector or the second element of my vector. So when you use a code like this, the result of A will not be independent from the identity of the vector because you are directly using the values in this vector. You're not just using this vector to define the number of iterations. So when you do this, you can, oops, let's run this again. And yeah. Okay, now you can see that I'm using the identity of these elements. So it's not just 1, 2, 3, 4, but I'm using the first element 3 and the second element 5 and so on. I briefly showed you can use break and next statements inside your for loops. Let's see an example of that. Here I have a for loop. I say I will take the values of 1 to 10, but I want to define a break statement. And I do this using if. I say if I is equal to 7, I want to print a message. I want to say terminating the loop since the number is I, which is 7, and then break it. So just terminate the loop and don't run it more. So when I do this, you can see that first it printed the values for all I values, but when it comes to 7, it just terminated the loop due to break and didn't continue with 8. But if you only want to skip one iteration and continue with the next cycle instead of terminating something, you can use the next statement. Here I say I want that I will change from 1 to 5, but if I is equal to 2, I just want to skip this cycle. I don't want to run the remaining of the code, and I just want to continue with 3. So when I do this, it will print the I times I values for 1, 2. I'm sorry, not for 2. It does it for 1, and for 2, it doesn't run it and just continue with 3, 4, and 5. So I just skipped one cycle. And let's see another version of this next statement. I just changed the place of print I times I, and then put the if and next statement. And when I do this, it actually didn't skip anything. Yeah, it run this code, and when it is I is equal to 2, it didn't run this for loop more and just like skip to the next cycle. But after next, there's nothing. So it doesn't make sense to use the next at the end of the loop, because I actually didn't skip anything. But here, because the next statement was before the actual job that I'm doing, it skipped one iteration. So when you're using next and break, you need to be careful about where to put these statements. The place will be really important for your procedure. All right, let's do another example. I just want to write a conditional statement that checks if I'm eligible for scholarship or not. And I want to do this for several grades. I want to do this for a couple of different grades. And it doesn't make sense to do this one by one for each grade by updating the value. I can just simply put them in a for loop. So first I create my for loop and I say my grade will take the values in this sequence. And for each of them, I will run these quotes. So here it checks if my grade is larger than 550, it means my grade is eligible for full scholarship. And if it is not true, it will continue with the next condition for, that I indicated with else if and control this. If it is not true again, it will check the next one. And if none of them is true, it will just run the else statement. Everything is the same as we did before. So when I do this, it just prints these statements for each grade variable that it iterates over. So now let's do another exercise. And here I want to take a number as input from the user. So again, I can use this code. So when I just run this, it gives me a prompt on the console. It asks me to write a number. Let's say it's 6. And then I say if the number is negative, I want to print a message that says, sorry, factorial doesn't exist for negative numbers. If the number is 0, I want to print a message that says the factorial of 0 is 1. And if number is greater than 0, I want to calculate the factorial of this number and print it. So now you need to think about how would you define a factorial using the for loop. Let's just first basically think what is a factorial and then think how would you put this or how would you express this in a for loop. Again, I'll wait for 2 minutes for you to try on your own first, or if you don't want to try to write it, you can just think how would you do this. Then we will go over the solution together. All right, let's go over the solution together. Here, what we will do to calculate factorial is very similar to the idea of using a counter variable. Because let's say you want to calculate the factorial of 5. What you will do is calculating 5 times 4 times 3 times 2 times 1. So actually it is pretty similar to what we do with a for loop. We want to iterate over different numbers starting from 1 to and go to the maximum number that we are aiming and multiply all of them. And by using a counter variable or a variable that we will keep track of the factorial, we can keep this variable and multiply the new value with this factorial and update the value of factorial in each iteration. So let's see how it will work. First, I ask for a number and I just type 6. You can type anything. I need to initiate the factorial variable outside of the loop. And now I'm initiating it as 1 because we will do a multiplication. And I know that the factorial of 0 or 1 will be 1. So I want the starting point of 1 to keep track of my factorial. I run this. And then first I'm doing the more simple thing that I don't need to come up with a solution. I just say if the number is smaller than 0, I'll just print sorry, factorial doesn't exist for negative numbers. Then I'll check another condition. If the number is 0, I will print the factorial of 0 is 1. Else, if the factorial is a positive number that I can calculate, I'll use a for loop. And I'll use this initiated factorial variable to update what is my factorial for a number. So I say, I will take the values of 1 to this number. And each iteration, I will update the current value of factorial by multiplying the previous value with I. So I start with 1. And when in the first iteration, I will be 1. So my factorial for number 1 will be 1 times 1. In the second iteration, I will be 2. So now I will update the value of my factorial as 2 times 1, which will be 2. In the third iteration, my value of I will be 3. And I have my factorial that is 2, and then I'll multiply 2 and 3 and find 6 as my factorial. And it will go until I reach to the number that I want to find the factorial of. So when I run this, it shows me the factorial of 6 is that. So it start from 1 and then multiply with each new iteration value, each new I value until it reaches to 6. Now we will continue with our last topic, writing functions. So I'm switching to my slides here. So, you know, in R, there are so many built-in functions or so many different functions and different packages that you can use. But sometimes you want to create your own functions. It can be something like the examples that we do. You want to calculate something weird, probably for the exercises we do. You may think that why would I even want to find the number of odd numbers, but they're just for making you ready for the actual problems you may want to solve. So in your data, you may want to solve a specific problem, and you may need to create a function for this. So you can use this function with different data sets. You don't want to repeat the same operations again and again for different times, for different data sets, for different experiments. If you know that this is a procedure that you will need to do over and over again, you can just save it as a function and then call this as you just used any function that is built in an R. And maybe you can create your own packages by combining the related functions. So to create your functions, first thing you do is defining a name for this function. So you can just like give any name you want. And then this arrow means, okay, now I'm defining this variable. And then I say function, which tells R, okay, now I'm defining a function. In the parentheses, you define the argument that you will use in this function. As you know, in the built-in functions, it has some inputs that you give to this function, and it uses them to create some output. So when you write your own function, you define these arguments. What are the variables or the values that will be used when doing the calculations or when running the processes for this function? And the order will be important because you will need to use the same order when you are calling the function again, or you need to use the argument names, which we will see some examples in a minute. And then whenever that function is called, R is just executing the statement inside the curly brackets. And you define an output value with return, which R will return as the result of this function. And the internal statements in the body of this function, so the statements that you define will remain invisible to the user because they're just run in a temporary local environment. And after you run the code, after you call the function, they just disappear. They are not stored. And only the final result, this result that you return using the return function, will be stored. And you can create, as I said, your own functions that you will use later. And after you create your functions, you can just save them in an R script, and then you can call them back using a source function. So when you call them back, it will mean that these functions are loaded to your computer again, just as you load a package using the library function. And then you can use these functions again. So again, the question is the same. Do we really write functions? Isn't the functions that we have from other packages enough? It may be enough for some of the, like for some people, if you don't need to do something more like custom based, maybe it will be enough. But for so many times, it is really useful to write your own functions, and I use them a lot because let's say I have a specific data cleaning procedure, or I have a specific outlier elimination procedure, and I know that I'll run the same procedure for different experiments or for different participants, and I want to just save these functions instead of copy pasting, and then I can use these functions again when I need them. Here's a example from a package. Here, someone just created a function that calculates and normalizes data. It just like normalize the data you have. And this person knows that this normalization procedure will be used a lot. So why would we just like run the same codes again and again when we need that, instead of just putting this into a function and then calling these functions much easier? So we can just create these functions, save them in our files, our scripts, then call them back using resource. Let's do some exercise in R again. I'm switching to my R code. All right. So let's create some functions and talk about these examples. First, I want to create a function that will take one input and then multiply the value of this input by 4 and return the quadruple value. First, I define the name of this function, and after the arrow, I say it's a function. And then in the parentheses, I just give the argument that the input that will be used in this function. Then I say I want to define a new variable quad, which will be x times 4. And then I want to return this value. So this will be my output. When I run this code, I can see this function in my global environment. And when you click that, you can also see what is inside this function. So you're basically creating a new variable, which is a function variable that you can see when you ask the class of it that you can use later. So because I have this function now, I can just ask the quadruple of 5 and it will return the value to me. What would happen if I ask about the quad, which is an internal statement in this function? So when I ask this, it just gives me an error and it says we don't have an object called quad, because as I mentioned, the internal statements are just temporarily executed in a local environment, not in the global environment. So after the function is called, we only reach out to the return value, the output value, and the remaining other parts are just like lost. Let's create another function that takes the wide power of x. So I define two arguments, x and y, and you can see that here I said y is equal to 1. When you define a value for an argument, it means that you are giving a default value to this argument. So it just calculates the wide power of x, define this as out, and then return this value. So it has two arguments, x and y, but because we defined the default value of y, it means that we don't have to type what is y all the time. If we don't type a value, it will just use the default value. So now I can just call for the fourth power of 3 and it will give me the result. And when I don't use the name of these arguments, which are x and y, R just assumes I'm using the original order. So when I don't say x and y, it means that the first argument is x and the second argument is y. But if you type the names of these arguments, you can call them in an order. So you can first type y and then x. But if you know the order, you don't need to use the argument names. And here I just say call 3. So I just call the variable x, but I don't type anything for y, which is y has a default value. So when I do this, it just shows me the first power of 3 because I didn't type what is y, it just used the default value. But because x doesn't have a default value, I always need to type input for x. So when I say how y is 5, it gives me an error again and says argument x is missing with no default value. So it doesn't know what to do when there's no x. So let's do another example. We want to write a function that takes the square root of a number and gives the rounded result. So the user will define the number of digits that the result is rounded. First, I give a name to this function. Then I define my arguments. The first argument is x, just a number. And the second argument is digits. And I also defined a default value, which is 0. Then I calculated the square root of this x. Square root is just a built-in function in R. And then I used, again, a built-in round function in R that I use the square-rooted number using the digits. So when I do this and call round squared 5, it will just give me the rounded square root using the digits 0. But when I define the digits, it gives me the rounded value of this number square root using 3 digits. Another concept that I want to show you is the use of three dots as the arguments. This three dot is a special construct in R that we use with function, and it allows user to enter as many inputs as they like. So if you want to have a function that doesn't have a fixed number of inputs, but it can be any number, you can just type function and then three dots inside the parentheses, and it will allow user to put as many input as they like. So for instance, we can create a function that will double the max value of a vector. So you are not restricting that there will be 5 values or there will be 10 values, but they can give as many values, as many integers as they want. And here I say use the max function and then use all of these objects the user gave, and then just double it and return the output. Now, using this function, I can just give as many input as I like. I don't have a restriction, and sometimes it is useful. As we saw, we can nest conditionals and for loops together. We can also use for loops and if-else statements inside our functions, which will be very useful. So this is not an example that makes sense, like why would you do that? But just to show you an example, here I have a function called my function, and it has a variable x. And then I say, I will do some, I will run some statements, but I want to run some statements depending on some conditions. So I say if x is greater than 0, so if it's a positive number, y will be x times x times x, and I will just return this value. And else if, control another condition, if x is 0, I want to give a warning that says value shouldn't be 0. Else, so if it's a negative number, again, I want to calculate x times x times x, but I want to calculate the absolute value of it and then return it. Here, something that you can notice in the first part, first I defined y, and then I say return y. But in this section, I didn't define y or z any value, but I directly put the output that I want to return inside the return. So sometimes it is just more convenient to first define the output and then say return this output. It may make it more like readable, but sometimes when you do something simple, you can just directly put the output inside return. So you don't need to do this step by step. So let's run this code and then test with some values, and we can see that it just run the calculated the x times x times x and then return this value. When it is x, it gave me a warning, and when it is negative, it just gave me the absolute value. And another concept that is really useful when you create functions is using recursive functions. These are the functions that call itself. And again, let's consider factorial to understand them. When you are calculating the factorial of 5, you can say that 5 times 4 times 3 times 2 times 1. But you can also say 5 factorial is equal to 5 times 4 factorial. So if you define a factorial function to calculate the factorial of n, you can actually just call the factorial of n minus 1. And then you can continue to do this until you reach to the final termination point, which is 1 here. So let's define a recursive factorial function. Here, again, I say function and x, so x will be my input. And then I say if x is equal to 0, just return 1. Here, again, you can see I just directly give the value that I wanted to return inside the return. And I didn't even do something like return A. It doesn't need to be an object. It can be a direct value. Else, I want to return the x multiplied by recursive factorial x minus 1. So I want to call this function again inside this function. So it will goes back and it will calculate the recursive factorial x minus 1 and then multiply it with x and return the value to me. So let's say that I called recursive factorial 3. It will give me the value 3 times recursive factorial 2. Then you are like opening a little tab for recursive factorial 2, which will be equal to 2 times recursive factorial 1. And then it will open another tab. It will say it is equal to 1 times recursive factorial 0. And when you reach out to recursive factorial 0, which will return 1, you will be ending this cycle of calling 1 previous. So let's run this and then try it with some values that we can see. It just calculates the factorial and give us the result. So when you're using this recursive factorials, as I mentioned, the termination point is so critical because we want that if x is 0, we don't want to call the recursive factorial x minus 1. We don't want to call recursive factorial negative 1. There should be a termination point that will stop this recalling to this function again and again. And when you're working with large data sets, this recursive functions are not always useful because, as you can imagine, it takes a lot of memory space if you are working with a large data set because you're opening a little window for each call. It calls recursive factorial 4, and then it calls another one and another one. So if you are doing something bigger, it might be not very efficient and may take lots of time and memory space. All right, oops. So we have another exercise here. Here it asks us to write a function that takes the age as input and then return the education level according to this age. So it will return either preschool, primary school, high school, or university, depending on the age. And we want to have this if else statement inside a function that we can use later. Again, I'll give you 2 minutes for you to try it on your own, then we will look at the solution together. All right, let's look at the solution together. Basically, I first define a name for this function, and then I give one input, the one argument for this function that will be my age. And then I say inside these curly brackets what to do with this x value, and I put lots of else if statements to control what should be the return value depending on the age. If it is smaller than 6, it will be preschool. If it is not true, it will check the second statement, and if it is true, it will return primary school, and so on. And something you may notice here is I didn't say if x is between 6 and 14. I just say if x is smaller than 14. And the reason is because it goes one by one, it checks the first condition first. And if it is not correct, if it is false, then it continue with the second condition. So if we are checking the condition here, it means that it is already larger than 6. So I don't need to write this again. And let me run this code and then check this with a couple of different values to see if it works. And it looks like, okay. The next exercise, we have a slightly harder one because you need to think about how would you solve this problem maybe more. Here it asks that we want to write a function that checks if an object is element of a vector. So I want to have two arguments. One will be the vector and one will be an object. And I want to say true or false depending on if the vector is one of the elements of this, if the object is one of the elements of this vector, so if there's any match. We already have a built-in function for this in R, which is like this, and it tells us if there's a membership or not. But now we want to solve this problem on our own because, as I said, you may think that we don't need to solve this problem. We don't have this problem, but you will have so many different type of problems with your data. And by doing some exercises that you wouldn't actually need, you just prepare yourself for how would you solve a problem if you don't have any other functions in R. So for this exercise, again, I'll wait for 2 minutes and then we will look at the solution together, and probably it will be the last exercise we can do. All right. All right, let's continue with the solution. So let's think, how would you understand if an object is an element of a vector? A basic thing to do would be just comparing this object with all the elements of the vector one by one, and just checking if this object is the first element of the vector. It is not, okay, then just like continue with the second element and compare if there's a match. If it is still not, just continue with the next element until you compare all the elements, or until you find a value that matches. So we will just basically do that. We will say, I want to create a function called membership, and it will have two arguments, data and object. And I want to iterate over 1 to the length of data. So we are not limited to a certain number of iterations. We want to check all the members of this vector, whichever the length is. And then I will look at the elements of data one by one and see if it is equal to the object I have. So in the first iteration, I will just look at data one, so the first element of this data, and compare this with my object. If it is true, if it is equal to my object, I will return the value true and just end the function. I don't need to look at the remaining values, because it just asks if it's an element, if there's a membership. And if it is not true, I will continue with the second iteration, and I will say if I is equal to, when I is equal to 2, so the second element of data is equal to object. If it is true, again, I will return the value true. And then I'll do this for all of them one by one. And at the end, I will return either true or false, depending on if I have any match. So when I run this code and then control this with a vector and an object, give me the response true, because I have a membership in this. There's a match between my object and one of the elements, or the two of the elements here. There are some different versions of this, and let me quickly show you. So here I just checked if there's a membership or not at all. And now the only thing I do is replacing the return with print. So now when I run this code and test the same statement, I will see that it just control it for each element one by one, and then return true or false for each of them. So it controlled the first element if it's the same as my object, and then tell me it is true. And then the second element of the vector and tell me if it is false. So it does a different type of work here. When I use print, it prints the value in each iteration, but when I use return, it only returns the final value and does this only for one time. And they are different in their nature, because a function requires a return value as the output. When you just use print but not return, it is not creating a copy of this response. So when I do this, I can assign this value, because I have an output here, to an object. And then I call this object, which will give me the response true. But when I use the print value, let's run this again and try to assign this to an object, it prints all of these values. But when I try to call the object again, it tells null, because we didn't create a return value here. We didn't create an output value. We just printed some statements, but because they're inside the function, they just disappear after we run this function. So to be able to store a variable, we need to use the return function. And we couldn't have time for them, but I have some other exercises that I explain how can you use print and return in different ways, and how can you make that a test that will test the membership for each object one by one, and then return the whole vector. So you can check them out later. I'll quickly switch to here to show you my email address. Thank you so much for joining today. I have lots of more exercises, so please check them later if you want to learn more about them. And if you have any questions about them, you can just write me anytime you want. And after the exercises, I also have some extras that I mentioned, which are while loop and some implicit loops. I knew that I will not be able to cover them, but I still wanted to add them so you can have a general idea about them. I have some explanations both in the slides and also in the our markdown file. So please take a look at them, and you can just ask me any question if you want. And thank you so much for joining.